Morning, Eddie. How you doing?
Back when we saw dans zone scolaire, sur ma soeur pour une écolière, so j'ai dit un saut, pas de collège, let's go. Mais là, il me book pour un show, I guess worse than life. Tout ce que je fais, je l'étais jeune, that's the best rapper alive, baby, it's all real. All real enough, boys brought on to gotta fill my cup. It's gonna love the V with you, some money screaming up the name, baby, it's all real enough. Boys brought on to gotta fill my cup. It's gonna love the V with you, some money screaming up the name, baby, it's all.
Can't step back, fait classe pour la jeunesse, complètement perdu. Le cocktail de drogue dans cette défi. Une fascination pour l'excès, mais tu dis, je suis des take pics. Trop de cash, can't spill it. Zero cuentos, minimum painkillers. Dropped out flexes, screaming for all my exes. That's who. About it, a minute I crack. La balance d'une puissance des crimes, on est mad. Le surhomme de niche m'applaudit, fait dans le dégât. Shidari, my man m'appelle jeune gâteau. You think general kill not, say it. 45K for the piece. Right around a drop top cat, bitch. And I got cocaine for the whole week, goddamn it. It's so much shit that you catch, shit is shut. All black, shit is shut. Eyes on the prize for the clear white line. The vibe from the flag and the tank cap five. She the best though. Back de la benzo, she give me neck though. Champagne night, that's a belt on mon neck d'or. Vente la Montréal, que l'espoir, merci bonsoir.
Back when we sold smoke dans zone scolaire, sur ma soeur pour une écolière, so j'ai dit un saut, pas de collège, let's go. Mais là, il me book pour un show, I guess worse than life. Tout ce que je fais, je l'étais jeune, that's the best rapper alive, baby, it's all real. All real enough, boys brought on to gotta fill my cup. Gonna love the V with you, some money screaming up the name, baby, it's all real. All real enough, boys brought on to gotta fill my cup. Gonna love the V with you, some money screaming up the name, baby, it's all real. Champ, started from the bottom, more baby, share, no we here. I gotta take a chance. These self-made men, you won't make themselves play ball with the label, low level, back with your posse, pay me that start money. Man, I crois que j'ai de la stage life, ça jouer live, la chaîne est éternelle comme. J'ballais, tu devais savoir depuis le temps qu'on est là-dessus. Une couple de bad girls, des bottles, des capsules, tu me faxes la facture. I'm on that red shit qui se boite seul, and I ain't sharing rien cher, et que je viens de dire, ça se boite seul, you should know. Tout le monde avait prédit que j'allais finir mal, j'ai des excuses de mes ex-girls, c'est drôle comment c'était moi le loser, now they can't win me back, getting X's and O's for mes exes and hoes, je suis donné des guests, des textes, des mots, let you know it ain't personal, mais tu sais qu'on fait ça comme personne d'autre, I still give it to you. Back when we sold smoke dans zone scolaire, sur ma soeur pour une écolière, so j'ai dit un saut, pas de collège, let's go. Mais là, il me book pour un show, I guess worse than life. Tout ce que je fais, je l'étais jeune, that's the best rapper alive, baby, it's all real. All real enough, boys brought on to gotta fill my cup. It's gonna love the V with you, some money screaming up the name, baby, it's all real. All real enough, boys brought on to gotta fill my cup. It's gonna love the V with you, some money screaming up the name, baby, it's all real.
Morning, everyone. For those of you who wanted me to do some questions, I'll need you to tell me what they are. Let's start with Gabrielle's question. For those asking, the song was XOXO by Loud Larry Aegis. I mean, they broke up a couple of years ago. Loud may be the most famous rapper in Quebec right now. And so this was Loud with Larry Kidd and Aegis. Loud had a huge hit maybe a year ago or two. Let's have a look at Gabrielle's question here. Limit as x goes to 1, x to the a minus 1 over x to the b minus 1, where b is not 0. I mean, first thing you want to do when taking limits is to plug in. And if you plug in x equal to 1, since b is not 0, this is going to be 1. 1 minus 1 is 0. And on top, you do get 1 minus 1 as well, regardless of whether a is 0 or not. Right? So this is going to have the form 0 over 0. We're in a L'Hopital's rule setting. Differentiate. Derivative of the top. Derivative of the bottom. And as x goes to 1, regardless of what a and b are, these things are 1. So the limit is a over b. We're done. Sod wants to look at this question. We almost did it last time. We ran out of time, I think. Well, actually, this was number 55, so we wouldn't have done it. I think the one I wanted to do was arctan here, regardless. Ben, I'll need you to supply us with that question. So limit as x goes to 0. What is happening here? You know what happens. X goes to 0, so the whole thing goes to positive infinity. And tangent goes to 0. And you know the graph of tangent. And this also goes to infinity. So you have infinity minus infinity here. Very well. Well, I mean, you know it's an indeterminate form, but not a form where we can apply L'Hopital's rule. So let's put everything together. Maybe a common denominator here. Seems reasonable. And what happens now, if you plug in 0, tangent of 0 is 0, so everything is 0, you've got a 0 over 0. Exactly a L'Hopital's rule. Exactly a L'Hopital's rule setting. So we can differentiate the top, differentiate the bottom. Right here. Well, let me know. So derivative of the top, derivative of tangent is secant squared. Derivative of x is 1. Derivative of the denominator is a product, so product rule applies. Tangent x plus x secant squared. And if you plug in x equal to 0, secant of 0 is 1, 1 minus 1 is 0, tangent is 0, x is 0, everything is 0 again. Still a 0 over 0. Let's keep going. Andrew's asking why these things cancel out each other. They don't. But remember that we're taking a limit. So when x goes to 1, this is going to be 1. And so is this. And, I was looking through some of your midterms, and a lot of people, for some reason, don't write limits. Markers were lenient on the midterm. We will not be so lenient on the final. The limits have to appear. It's a fundamental part of the question. If you don't write limits, this is not equal to this. If the limits aren't there, it's completely wrong. Is this a loop? It's a valid question. It's too early to tell. And I mean, we started out with this and we have something completely different. So I wouldn't suspect this to be a loop. I mean, it's always in the back of your head, right? But I mean, doing l'hôpital once or twice or 3 times, it's not unheard of. Let's continue. I don't expect this to be a loop, right? Because things are changing, right? I mean, you started out with an x, now you've got a 1, and you know the next derivative, it's going to disappear. Khan's asking what happens if you keep getting 0 over 0, but it's not a loop. I mean, take this example. This is a good example, right? You start out with an x. So, I mean, forget this part because we had to rewrite it in a l'hôpital setting. So you have a tangent minus x. You differentiate once, you get a minus 1. It's still giving you a 0 over 0. Well, once you differentiate a second time, this thing will have disappeared. So this x will have disappeared. And I suspect that at some point, we're going to be okay. At some point, we're going to stop being in an indeterminate form. Derivative of secant squared to secant times the derivative of the inside. Derivative of secant is secant tan. Derivative of tangent is secant squared. Here, this is a product, so product rule applies. Derivative of x is 1. Now leave the x fixed, differentiate the secant squared, and derivative of secant squared is right here. So 2 secant squared tangent. And now you see, thanks to this, the denominator is not 0 anymore. The denominator is not 0, so you don't have a 0 over 0. Numerator is 0 though because of the tangent, and you're done. That's 0 over 2, which is 0. Convinced? Jack is asking if related rates requiring prior knowledge of physics will be on the final. No, we're not going to focus on those. What is this business? We were differentiating secant squared, but we noticed that we already differentiated secant squared in the numerator. So I'm just using this prior knowledge. JC, we're going to do that momentarily. All right, folks, while I do appreciate you asking questions, we could easily spend the whole day doing some questions, but we will run out of time and we have to get to some material. So here's what I propose. If you have questions, I have office hours tomorrow. Come to the office hours from 1 to 4, Burnside. Burnside 1127, 1 to 4. And we can address those there. Miriam was asking, why is it 2 on the bottom? Well, I mean, you get the 0 on top, right? Because tangent of 0 is 0. And tangent of 0 is 0. So this whole thing is 0. Well, I mean, you also have 0 there. And secant of 0 is 1. So 1 plus 1 is 2. Will related rates be a large portion of the final? I don't think so. You might expect 1 or 2 questions on related rates, no more. Did I mention I finally wrote the final? Well, I mean, I say I, but it was a joint effort. 12 multiple choice, 9 long answer. $21 in total. Thank you. When will the final be? I've posted a link to the final exam schedule. 12 multiple choice. Nine long answer. All right. Lynn, you should be able to. The final exam schedule is for all courses. So maybe there's an issue where were you using a phone? Was it a browser issue? I mean, I accessed it yesterday. There was no issue. Maybe try again using a different browser. But it gives you all the exams for all the courses. All right. Before we go back to L'Hôpital's rule, somehow I had forgotten to introduce a second derivative test. Locations should be there as well, are they not? I had forgotten to mention the second derivative test when we were looking at increasing and decreasing functions and concavity. Okay. Sorry. So second derivative test. Let's get to it. Suppose f double primed of x is continuous near C So location's not released yet, released next week. Thank you, Sarah. Here's what I expect. It's going to be in the gym. You can safely assume. I shouldn't say that. Let me take that back. I expect it to be in the gym. All right, second derivative test. There it is. So if your function has a horizontal tangent line and is concave up, then you have a local minimum. Exactly the gym. It's where It's essentially on the corner of Dr. Penfield and University. If you go up the hill on your right. Yeah. I mean, let's draw a picture of what's happening here, right? And this will give you an idea of the proof. If your function has second derivative positive, that means your function is concave up. And if it's a point where the slope of the tangent line is 0, boom, local minimum. Similarly, if the second derivative is negative, we saw this means concave down. And it's a point where the derivative is 0, so horizontal tangent line, local max. You're right. Sophia suggests that f prime of 0 doesn't necessarily mean there's a local max or min, but if in addition you have one of these two things, then yes, you do have either a local max or a local min. Well, exactly, as Sean suggests, right? I'm not a huge fan of the second derivative test. I'm not a huge fan of the second derivative test, and I'll show you why. Well, I mean, I'll tell you why right now, because it only gives local. You can only conclude local max and min. But as Sean suggests, when you generalize to higher dimensions, the idea of a first derivative chart is out the window. So you cannot figure out local max or min or absolute max or min this way. But there are versions of the second derivative test in higher dimensions. So this second derivative test generalizes to higher dimensions, whereas the idea of a first derivative chart does not. Did I take 19 down? That's odd. Let's take an example from the book so I've labeled this as number 19. I hope it is not. I hope it's number 20, but that's all I have for now. So we're going to have to work with that. Goes Pratik's question. How can the first derivative be 0, but the second derivative would not be 0 in terms of speed or acceleration? So you're saying, how can we have a speed of 0 and yet still have a positive acceleration? Imagine a car that you're going in reverse. So you have a negative velocity, and then you put it in drive, but you're still kind of moving backwards until you give it some gas, and then you start moving forward at some point. So you were moving backwards, the velocity is continuous. So at some point it must have been 0, but you are accelerating. That's the idea. All right, so if you were moving this way, and then, so with a negative velocity, and then you start moving that way, at some point, the speed must have been 0, but the acceleration was always positive. And as somebody suggests, if you throw a ball, there's always acceleration due to gravity acting on it. But at some point, when it reaches the highest level, the velocity is 0 before it starts coming back down. This is an even better example than the car. Very nice. All right. The question is asking us to classify the critical points using second derivative test versus first derivative chart. All right. So you know what to do, right? It's a polynomial. So continuous everywhere, differentiable everywhere, very nice. 6x minus 6x squared. If we factor out 6x, we get this, and we get critical points easily seen to be 0 and 1. These critical points are where the derivative is 0, right? You see that immediately. Take the second derivative, and what do we get? 6 minus 12x. So here, let me point out, f prime of 0 is 0, and f prime of 1 is also 0, right? Satisfying the second derivative test conditions. We have the second derivative. So at 0, this is 6, which is bigger than 0. So local min. And at 1, this is minus 6, which is less than 0, so local max. The question was asking us to do a first derivative chart as well and compare the two. So let's do it. We had critical points of 0 and 1. And if you take a negative number, this is going to be negative. 1 minus a negative number, this is going to be positive. So negative, positive, the whole thing is negative, which means your function is decreasing. If you take a number just slightly bigger than 0, this is going to be positive. A number slightly bigger than 0, this whole thing is going to be close to 1, so positive. Everything is positive. Your function is increasing. Again, you can plug in, you know a number between 0 and 1, right? 1/2, 1/3, whatever. Plug it in, and you'll get the answer. But sometimes these arguments are nice to make because we've seen examples where that happens. And if you take a number bigger than 1, this is going to be positive, and 1 minus a number bigger than 1 is negative. Again, right, don't assume it always changes signs. You know it doesn't necessarily. You have to check every single time. What's happening at 0? We have a local min. And what is happening at 1? Local max. Exactly the same conclusion as the second derivative test. Sometimes, though, the first derivative chart will give you absolute max min. Not always, but sometimes it does. Here we don't have enough information to conclude that, but certainly the answers agree. Sophia brings up an interesting point. If the first derivative chart is complicated numbers, is the second derivative test preferred? I would claim not necessarily, but I can see your point. If the second derivative is positive, if the second derivative is positive, you do have a local minimum, right? And Sophia is asking, what if the second derivative is 0? Well, then the second derivative test does not apply. It does not give you any information. You could have a local max, you could have local min, you might not have anything. In fact, if the second derivative is 0, you have a point of, well, no, I shouldn't say that. So as Sean suggests, in higher dimensions, what happens, you have this idea of saddle point, a very interesting idea. But yeah. When would someone use the second derivative test instead of the first derivative test? Well, first of all, if the question specifically asks to use the second derivative test, certainly you want to do that. Secondly, what if you did not have the actual function? What if you didn't have the actual function, but only knew its behavior at critical points? So in other words, if you knew f prime of 0 was 0, f prime of 1 was 0, and f double prime of 0 were 6 and negative 6 respectively, without knowing anything else about the function, without knowing that this was the function we were using or something else. You see, just by knowing the second derivative at these critical points, that's sufficient. So that's when you would use that specifically. You can always use it to check your answer as well, right? These are two different ways to conclude local max and min, so that's always nice. If a function has a vertical slope at a point, is that a point of inflection? Not necessarily. Not necessarily. Right? If you have something like this, these are both concave down, but you have a vertical slope at the point. All right, back to, it can be that the second derivative undefined is also a critical point. Well, critical points come from the first derivative, so maybe you meant the first derivative. So if the first derivative is undefined, then you also have a critical point, but the second derivative test does not apply here, because in the second derivative test, you need the first derivative to be 0. Right? So the second derivative test does not apply to all critical points. It only applies to the critical points where the derivative is 0. Let's go back to limits. Right, so some books make a distinction And I mean, you do that especially in higher dimensions between a critical point and a singular point. In one derivative, I mean, most books don't do that. So in the single variable case, we confuse them, but in higher dimensions, it's a good idea to distinguish between derivative being 0 and derivative not existing. Indeterminate forms, referring to limits, of course, we've seen several indeterminate forms, right? Important ones, 0 over 0 and infinity over infinity, ones where you can use L'Hopital's rule, very nice. But we had others, right? 0 times infinity, where we saw that this might be manipulated to bring it into a 0 over 0 or infinity over infinity, and then use L'Hopital's rule. But it's not necessarily the only way, but we've seen that happen. One of our first examples today was infinity minus infinity. So these are indeterminate forms, and again, you should have examples readily available to you to convince yourselves that anything can happen here. Now let's introduce 3 more indeterminate forms. 0 to the 0, infinity to the 0, 1 to the infinity. Let me, Pratik is asking, what about 0 over infinity? I claim this is not an indeterminate form, and as many people have been quick to answer, 0 over infinity is actually 0. So let's introduce 3 more indeterminate forms, all of whom are treated in exactly the same way. 0 to the 0, infinity to the 0, 1 to the infinity. Why are these indeterminate? Let me give you a simple argument. You're thinking to yourself, anything to the 0 is 1, but 0 to anything is 0. So is the answer 0 or is it 1? In fact, anything can happen. Similarly, anything to the 0 is 1, but infinity to any power is infinity. Or if you have negative powers, maybe 1 over infinity, which is 0. So what's going on here? Is the answer 0? Is the answer 1? We're not sure. 1 to the infinity, I mean, you're thinking to yourself, surely 1 to any power is 1. But keep in mind that this is as Kahn suggests, it's a limiting process, right? It's not the number 1, but something that's getting closer and closer to 1. So if something was bigger than 1 and you take larger and larger powers, this blows up to infinity. And if you take something less than 1, like a fraction, and you take larger and larger powers, that goes down to 0. So is the answer 0? Is the answer infinity? Is the answer 1? Because 1 to anything is 1. Who knows? Isaac is asking if negative infinity minus infinity is negative infinity. I mean, I think that's pretty clear, right? You can think of infinity as a very large number. So very large negative number plus another very large negative, you get a very large negative. What about 2 to the infinity? You know what 2 to the infinity is, right? Sarah's asking, does this work for any constant? It does not. It does not. It really only for 1 is this an issue. So how are these treated? Right? I mean, the problem is with the powers. The problem is with the powers. And, you know, I mean, it's difficult to work with powers that are ever changing. So let's get rid of the powers by taking A logarithm. Logarithms allow you to bring powers down. Zoe's not convinced with the 1 to the infinity. Again, keep in mind, it's not the number 1, right? But it's something that goes to 1. So if this was just a bit larger than 1, and you're taking very large powers, I mean, before, who was it? That was, Sarah was suggesting 2. If this was 2 to the infinity, it would be infinity. Right? If it's 1.5 to the infinity, it's still infinity. Right? So if it's something just slightly bigger than 1 and you take larger and larger powers, it blows up. If it's something less than 1, like a fraction, and you take larger and larger powers, it goes down to 0. So is the answer 0? Is the answer infinity? Is the answer 1? Because 1 to any power is 1. Right? It's because of the limits. It's not the number 1, but rather something that behaves like 1, something that goes to 1. Let's take some examples, and you'll see. Right, so my suggestion was, by taking a log, this will allow you to bring the power down, and then you can work with it. Case in point. As x goes to 0, what's happening here? So what page is that from? 316. So limit as x goes to 0 from the right. What is happening? You know tangent of 0 is 0. So this has the form 0 to 0. And exactly, Kripa is asking if this applies to questions like x to the square root of x, and it exactly does, right? That will have the form 0 to the 0. So I'm suggesting that we're going to start by taking a log to help us evaluate this by taking the power down. Well, now you're thinking to yourself, how can you just take a log? Aren't you changing the question? And indeed we are. These two things are not equal. I've not put an equal sign here because they're not equal. We're changing the question. We're taking a logarithm. This is not the same question. But bear with me. If we take the log, this allows us to bring the power down. And now, as x goes to 0, this goes to 0. Tangent log of 0 is negative infinity times 0. So this has the form infinity times 0. Still indeterminate, but now something you're more familiar with. Something that you can tackle. L'Hopital's rule, yes, eventually, but not right away, right? Because this is not in L'Hopital's rule form, but you know you can make it very nice, as Eddie suggests, we're going to rewrite this as ln over 1 over x. Right? We saw last time that x is equal to 1 over x. A very nice trick. Very useful. Why is ln of 0 infinity? You know the graph of ln. As x goes to 0, your function goes to negative infinity. Right? So our usual trick, Sophia is correct, ln of 0 is negative infinity. Fine, if you want to put a negative there, it doesn't matter, right? I mean, this is just for your sake, right? I'm putting it in brackets. It's only to understand what form you're working with. As x goes to 0, tangent of 0 is 0, ln of 0 is negative infinity if you want it. And this goes to 0, 1 over 0 is infinity, and everything is positive. I mean, the plus or the minus really doesn't make a difference here, right? The only important thing is that we have an infinity over infinity. Whether it's positive or negative, either case makes no difference. L'Hopital's rule works in all of these situations. So we have an infinity over infinity. We can apply L'Hopital's rule. Let's do it. Derivative of the ln is 1 over. So 1 over tangent times the derivative of the inside. What's inside? Tangent, whose derivative is secant squared, times the derivative of the inside. What's inside? 2x, whose derivative is 2. Derivative of 1 over x, negative 1 over x squared. Very nice. Let's clean that up by, you're dividing by this. Let's multiply by the reciprocal. Negative 2x squared secant squared over tangent squared. Oh, no, not tangent squared, but just tangent. All right. Fine. I mean, you could clean that up. Are you taking the limit of the power after writing the original? Exactly. Exactly, JC. How did we get 1 over x? Eddie has answered that, right? We saw last time that x is the same as 1 over x. This was a nice trick that is important, very useful. And then we made use of that right here. Pratik is saying 0 over infinity is 0, correct? But I don't think we have that here. I think we have still a 0 over 0. Do we not have to use a quotient or product rule? Claire brings up an interesting question. Do not confuse L'Hopital's rule with the quotient rule. We're not taking the derivative of the function, right? No, there is no theorem that tells you the limit of a function is equal to the limit of its derivative. And that's because it usually isn't. So we're not differentiating this. But if you have a limit that has the form infinity over infinity, L'Hopital's rule says you can differentiate the top and you can differentiate the bottom, and the limits remain the same. So be very careful not to confuse L'Hopital's rule and derivative / quotient rule. Pratik is saying, what about the step before bringing x squared up? Okay, what about this? What was the issue here? Right. Is that right? In this case, I think we have infinity over infinity, right? Tangent of 0 is 0, so this is going to be some sort of infinity, and everything here is fine. So we have infinity over infinity there. Yeah. Why is it not the limit of its derivative, but it is the limit of the derivatives of top and bottom, right, Con? And that's because of L'Hopital's rule. We proved L'Hopital's rule, not in the case infinity over infinity, because it's a bit more technical, but in the case of 0 over 0, though. So we've convinced ourselves of the 0 over 0. Exactly that. Connor has hit the nail on the head there. All right, let's finish that up. We have a 0 over 0. You could simplify this. It does simplify. But let's not waste any time simplifying it, and let's just do L'Hopital's rule. Why would you jump to that right away? You know what the derivative of tangent is. It's secant squared. And then it's not going to be 0 anymore. So one more L'Hopital's rule, and you're good to go. Ben is asking, are we allowed to use L'Hopital's rule for every exam question? You know L'Hopital's rule doesn't answer every single question. I'm just saying. The other techniques are very important because L'Hopital's rule, while a very powerful tool, does not answer every single question. Derivative of tangent is secant squared. Jesse is asking a very important question. Why are we allowed to take ln in the first place? Aren't we changing the question? We are, but let's just finish up the limit of the ln and we'll discuss that in a moment. And I think it's easy to see that the whole limit is 0. Right? Does everybody see that? And as Shear suggests, right, here we evaluated the limit of the ln, and we got 0. So now we have to compensate. 0 over 2 over 0, thank you. So now we have to compensate, right? We evaluated the limit of the ln. How do I go back to the original? And you know that exponentials and logarithms are inverse functions of each other, right? So e to the ln x, this simplifies to x because this is the composition of the exponential and the logarithm, a function and its inverse. We evaluated this when we wanted this. So all we have to do is raise everything to the exponential. We have a limit of 0. So our original limit is e to the 0. Right? If I wanted these two things to be equal, I could have put an e here. e to the ln blah, blah, blah is equal to that, right? The ln and the exponential cancel out. But then you would have had to carry around the e all the time. Nobody does that. So they just take the ln, knowing that in the end you're going to raise everything to the exponential. And you know that you're allowed to do this by limit properties, right? Limit of e to the function is e to the limit of the function, right? Because the exponential is continuous. The continuity of the exponential plays a role here. Juan suggests other methods you could, right? I mean, you could write this as sine over cosine, cancel one of the cosines, x over sine. You know something could be done here. And Yassine suggests yet another approach. There are several things that could have been done, absolutely. Ben is asking a question. I'm not sure what your question is, Ben. Are you still with the L'Hopital's rule on every exam question business? Right. So all that to say, there were several other approaches you could have done, but in the end, a limit of 0 is what you would have gotten. So we compensate by having taken a ln, by taking the exponential, and there's our answer. Let's try a few more, just to get you started. I know we're quickly running out of time. There's no need to mention anything you've seen. It's really just the way we do it. I mean, the continuity I'm mentioning to you to justify what we've done. But now that it's been justified, we're good to go. Ben is asking, where did the e come from? We started by taking the limit of the ln. Limit of the ln is what we evaluated when we really wanted this. So how do we compensate? How do we get rid of the ln? By raising everything to the exponential. These cancel out. Let's try another one. As x goes to infinity, you see what's happening. As x goes to infinity, this goes to 0. So this has the form 1 to the infinity. I guess b should not be 0. Let's assume, why are there 2 secant? Because it's the derivative of secant squared, right? So we differentiate the square first. So we get 2 secant, and then we differentiate the inside. The derivative of secant is secant tan. So the answer for the previous is still 0. No, it's not 0. It's e to the 0. Right? We evaluated the limit of the ln. The limit of the ln is 0. So now we take the exponential to cancel, to compensate for having taken a ln. What if a is equal to infinity? I think it's really understood that a and b are constants, real numbers. So let a and b be real numbers. Then this is going to have the form 1 to the infinity. We treat it exactly in the same way that we treated the 0 to the 0, or the infinity to the 0, which we haven't done yet, but regardless, we'll take a ln. This allows us to bring the power down. Again, notice that these two things are not equal. I'm changing the question by taking a line. As x goes to infinity, this goes to infinity. This goes to 0. Ln of 1 is 0, so this has the form infinity times 0. B is a constant. Maybe I can take it out. And the 0 times infinity, you know what to do with that. Same trick we did before. X is 1 over x. And now as x goes to infinity, this goes to 0. Ln of 1 is 0. This goes to 0. So we have a 0 over 0. Ready for L'Hopital's rule. Derivative of the ln is 1 over times the derivative of the inside. Derivative of 1 is 0. Derivative of this is negative a over x squared. Derivative of the bottom, negative 1 over x squared. These cancel out nicely. And as x goes to infinity, this goes to 0, leaving us with AB. Is there not a limit rule that applies for all indeterminate forms? I don't believe there is. Jake is asking, can we always take ln? You want to take ln in these three cases. 0 to the 0, infinity to the 0, 1 to the infinity. I mean, you can essentially always take ln as long as it's applicable, right? You don't want to be taking ln of a negative number. So as long as it doesn't go into the negative region, you're really fine with taking ln. It might not help you in all cases, but in these three cases, it helps you because it brings the powers down. I only cancel the negatives and the x squares. The a is still there. All right, so the negatives cancel and the x squares cancel. So we have a limit of AB. Consequently, this limit, we start by taking ln. We're going to compensate by raising everything to the exponential, e to the AB. Or maybe you want to write it here. Jake is asking, in these three cases, can we always take ln? The answer is essentially yes. Can you add in the extra step at the very end? I keep getting just B. I mean, what happened with the A here? Did you cancel the A? The A is still here. The A is still here. If the error is asking if it will ever loop, who knows? Who knows? I guess it's technically possible. I've never seen that happen. Why do you go back to the original expression to raise to the exponential. Well, I mean, this is the original question. This is the question we want to answer. This ax goes to 0, but we cancel the x squares here. So now you're just left with an a on top. Right? I mean, this is the question that we're asked to solve. So you have to solve that. We answer the question, what if you took a ln to begin with? But we're changing the question. We're not taking this limit, we're taking the limit of the ln. So we have to compensate by taking the exponential of the answer we get. So all of that is to find only the power of 3. I'm not sure what 3 you're referring to, but this limit is what we were looking for. How are we doing? We haven't seen an example of infinity to the 0. Do we want to do that? Or you guys can work that out in exactly the same way? I know we've extended our welcome. It's not b over x, right? It's b times x. It's b times x. Let's do one more for those who can still stick around. Exactly. As Connor suggests, the book pointed out that if a and b are 1, that limit is really the definition of e. So with an a there and b there, it changes to e to the ab. So the final answer is e to the ab. Exactly. Bree's asking to do more on Friday. I think we've essentially done most of the examples in the book if we throw this one in. On Friday we're going to start graphing. Because, you know, I mean, we are running out of time, so we have to finish the material. But look, I mean, you have the required tools. These 3 indeterminate forms are all treated in exactly the same way. You start by taking a ln, evaluate the limit of the ln, and then compensate by raising the answer to the exponential. Here, what are we looking at? As x goes to infinity, e to the negative infinity is 0, so this has the form infinity to the 0. Yet another indeterminate form. We're going to start by taking the limit of the ln. They're not equal, right? Again, they're not equal. We're changing the question. Exactly that. Exactly as Elliot suggests. Have a look at Elliot's post. That's exactly what we're doing. We're evaluating ln of something, but we wanted the something to begin with, right? We wanted this. We're evaluating ln of that, and then we compensate by taking the exponential, because exponentials and logarithms cancel themselves out. Taking a ln allows us to bring the power down. So this is e to the minus x, ln x. As x goes to infinity, ln of infinity is infinity. E to the negative infinity is 0. So this has the form 0 times infinity, an indeterminate form. that you're familiar with. We need to manipulate this. And the negative exponent here makes everything very simple. We can rewrite it this way. As x goes to infinity, now we have infinity over infinity. Now we're in a L'Hopital's rule setting. Derivative of the top, derivative of the bottom, or if you prefer, well, I mean, now we're in Pratique's setting, right? The 0 over infinity. If you're not comfortable with that, maybe you want to rewrite it as 1 over x, e to the x. And as x goes to infinity, you have 1 over infinity, which is 0. Could you take ln twice instead? Well, taking ln twice doesn't cancel taking ln twice, right? I mean, if x is 3 and you square it, how do you get back to 3? You don't want to square everything again, right? Because it's not going to compensate. What you want to do is the inverse operation. Right? You want to do the opposite of what you did. If you took ln, the opposite of ln is the exponential. So this limit is e to the 0, which is 1. Absolutely. So Sarah is suggesting, well, I mean, you wouldn't have that. You wouldn't have that because if you're taking ln of the whole thing again, ln of the sum is the sum of the lns, and as Fisher points out, you'd have a ln x, right? So this would be ln of e to the minus x plus ln of ln x. So this would be nice and simple, but now you've got a ln x business. And then you'd have to take the exponential twice. I mean, theoretically nothing wrong with that, but no need because this is easily evaluated anyways. What would happen here? You'd have to show that this goes to negative infinity. It's fairly easy to do that. Show that this goes to negative infinity, and then your answer would have been e to the negative infinity. E to the negative infinity is 0, e to the 0 is still 1. So it would have worked. It would have worked. It would have worked. Well, if you are, let's answer your question and then we'll end there. Limit as x goes to a. Post x ln x minus a over ln of e to the x minus e to the a. Is there any condition on a here? let's assume, right, because of the cosine here, let's assume for a moment that A is not an odd multiple of pi over 2, so that the cosine is actually not 0, right? Because then you'd have a 0 times infinity, and that might be questionable. We have to do more analysis on that for a moment. So if no condition on A was given, let's assume A is not that for a moment, and maybe we'll try to answer what happens if it is. But if A is not that, this is not going to be 0. So numerator goes to infinity, and denominator also goes to infinity. So we have an infinity over infinity. You can differentiate top and bottom. We're in the L'Hopital's setting here. Derivative of cos is negative sine. And then derivative of ln is 1 over. Derivative of ln is 1 over. Times the derivative of the inside. Why does it go to infinity? I mean, if you plug in, you get ln of 0, which you know to be infinity. It's negative infinity, right? If you want to be strict about it. And with the cosine, I mean, it could be negative or positive, so we don't even know. But it doesn't matter, because whether it's positive infinity or negative infinity over positive infinity or negative infinity, L'Hopital's rule will apply regardless. All right. Let's try to clean that up. Let me take out the 1 over e to the x business. Because that's not an issue, right? That's not doing anything terrible. Let's put a common denominator for the numerator. And since I'm dividing by this, let me multiply by the reciprocal, e to the x minus e to the a. Let me take it a step further. Let me rewrite this. The 1 over e to the x, again, not an issue. Let me combine these two things. So e to the x minus e to the a over x minus a. And then the rest. So cos x minus x minus a sine x ln x minus a. You have to take the derivative of e to the a. A is a constant, so the derivative of e to the a is 0. Sorry, this is e to the a. This you recognize, right? This you recognize. Do you recognize? Thank you, Bree. I've made the change. This you recognize. This is not an issue. That's not an issue. So the only issue is this. Right? So what is that? Let's look at that separately. X minus a ln of x minus a. Right? Very nice, Eddie. Eddie has recognized this as the derivative of e to the x at x equals a. Or one quick L'Hopital's rule will do it. So really the only question is, again, the sine x not playing an important role here. So the only thing that's worrisome is x minus a times ln of x minus a. As x goes to infinity, as x goes to a, this goes to 0. Ln of 0 is infinity, and this is 0. So it's 0 times infinity. So you know what you're going to do. You're going to rewrite this as ln x minus a over 1 over x minus a. And now this has the form infinity over infinity. So you can apply L'Hopital's rule. Derivative of ln is 1 over times the derivative of the inside. Derivative of that business is minus 1 over x minus a all squared. So when you flip it, you get negative x minus a, right? I mean, x minus a squared over x minus a. That cancels, leaving you with just one of them. And this negative carries forward. And this limit is easily seen to be 0. So this whole thing goes to 0. This whole thing, either L'Hopital's rule, quickly in your head, right? Because it has the form 0 over 0. Derivative of e to the x is e to the x. Derivative of x minus a is 1. So this is just e to the x. Limit as x goes to a, so that's going to be e to the a. This is 1 over e to the a. So these cancel out. This goes to 0, and we're left with cosine x, or cosine a. Very interesting. Very interesting. Now we should investigate what happens if this is that's actually not going to matter. That's not going to matter because you could have taken this out. Yeah. This limit will always exist regardless. So concentrate on this limit, which had the form infinity over infinity. There you go. There you go. Is it cos a over a? Do we have a 1 over a? Did we have a 1 over a? Am I missing a 1 over a somewhere? I don't think I am. Well, this limit here goes to 0, so you get sine x times 0, or sine a times 0, which is going to be 0. Very nice. Very nice. So I should have noticed that right away. Leave the cosine alone. So this doesn't even matter. You don't need to suppose anything. Leave the cosine alone. It would have been a simpler question. Put the cosine separate because this limit exists regardless. And this limit is going to have the form infinity over infinity. PR is asking why this limit goes to e to the a. Eddie noticed it as the definition of the derivative. So first of all, let me answer this. Eddie noticed it as the definition of the derivative. That's a very nice observation. If you don't see that, that's fine. Just do L'Hopital's rule on this part. If you do L'Hopital's rule on this part, right, because this has the form e to the a minus e to the a, so 0 over 0. You're in a L'Hopital's rule setting for this part, you can do that. And you're good to go. Yash is asking, how can we just calculate the limit of some parts? Well, you know that the limit of a product is the product of the limits, if all the limits exist, right? So here this limit exists, I can do that part separately. Here this limit exists, I can do that part separately. This limit exists, I can do that part separately. So really the question is, what about this limit that is not immediately clear? So that's why we did it separately. Boom, it exists. We're good to go. And how do we know how to suppose things? I made an assumption here that I actually did not even need to do. It was better to split it up. Why was I making this assumption? Because I was looking at these two things and I was thinking to myself, I've got infinity over infinity here. I can apply L'Hopital's rule. And that's true unless this was going to 0. In which case, I would have had 0 times infinity. And that's questionable. You cannot apply L'Hopital's rule in that setting. But if you take it out and apply L'Hopital's rule just to this part, this is always in the form infinity over infinity, and you're good to go. So you don't need to make any assumption. All right, I've kept you here way too long already. So you can split up the function and apply L'Hopital's rule to each separate part, absolutely, if the limit of each part actually exists, right? The ends justify the means. Shouldn't the e to the a cancel each other out? They do. They do. E to the a cancels with 1 over e to the a. That's why in your final answer, where did I write the final answer? Cosine A is all that remains. But how do we know cosine A won't be 0? You don't. You don't. And that's not an issue. The limit could be 0 if A was pi over 2. A very nice question. Very nice. I mean, it's easy to get lost in the work, but try it again. Try it again and do it the good way. Split it up as cosine x times this. The cosine x is not an issue because that limit exists immediately. Evaluate this limit and it's going to be easier. It's going to be easier, no assumption needs to be made, and you're good to go. All right, folks, thank you all for coming and staying until this late. I will see you guys on Friday, where we're going to put everything together now and graph functions. Yash is saying, since it can be 0, isn't pulling it out problematic? It is not, right? Because this limit here, what I'm suggesting is that this limit is going to be 1, regardless of what A is. So this limit here has the form infinity over infinity. You can apply L'Hopital's rule to this. And I claim that it's always going to be 1. It's a bit involved, but let's say that the final exam, this is as hard as it gets. It's not that difficult. I did not tackle it in the most efficient way, but I'm inviting you to do it now. Split it up into cosine times this, and just evaluate this limit. You'll see it's not that bad. Try it and let me know on Friday. And again, on Friday, we're putting everything together and using all of the calculus machinery that we've developed to graph functions. I don't know what page that was from. Vieira is the one that gave it to us. All right. Thank you, folks. You guys have a good day, and I will see you on Friday.